Hi, folks. Good morning. Today we're going to be talking about an integrals review. And so I know that some of us might feel super comfortable with integrals and others of us might feel like, ooh, I don't really know what happened the second half of 121, but we're going to take a moment to kind of make sure we're on the same page about what's important and what we hopefully can clarify some misunderstandings about. Okay, so let's get started. All right, integrals review. Skills for us to master. I really want us to understand the difference between a definite integral and an indefinite integral. I want us to be able to explain the concept of an integral, like what is it that we're finding? And lastly, I want us to, keywords here, correctly apply the power rule, exponential rule, log rule, and U substitution. Okay, so U substitution, pretty important here. I just want to point out that cannot be the one rule we don't know. I want that to be a rule that we feel really comfortable with because we're going to see it a lot, and it's actually going to be one of the first strategies we try for some of the more complicated integrals. All right. So here are some general formulas. All right, we've got our good old power rule over here. All right, and what's important to know about this power rule is that it is fine and good for all powers of x with one exception. Okay, anytime the power is -1, that is not something we can use the power rule for. Okay, so in this case, we actually want to use our natural log. All right. And then hopefully we remember the integral of e to the something, e to the u is just e to the u. Okay. So a couple properties of indefinite integrals here. If we have a constant in the front, we can go ahead and pull that constant out. All right. So we can call this sort of the constant multiple rule for integrals, right? And it just keeps our numbers a little bit smaller if we go ahead and pull that out to the front. All right, now turns out if we are adding or subtracting two functions, we can go ahead and split them up into multiple integrals. All right, so we're going to start to encounter questions where we might want to split them up because sometimes, let's say, we can do f of x, the integral, no problem, but when we get to g of x, we might need to use u sub or a different technique that we're going to learn. Okay, so even though in Calc 1, we don't really split integrals as much, it just might be something a little helpful for us to take a look at in this class. Okay. All right. So not a whole lot of pre-work talking today. We're just going to dive right in. I believe we've got 12 integral examples, and we'll kind of take a look at each one and see how it goes. All right. And again, if you want to pause the video at any point and then just kind of work on your own and then come back and check your answers, you can always use that as a strategy to help you feel like it's more like an interactive class. Okay. All right, let's go ahead and start with example 1. We've got the integral of 7x to the 6th. Now, we don't have to, but I'm going to go ahead and pull that 7 out to the front just so we can see what we mean by that constant multiple rule from the previous page. Okay, so 7 is a constant. I can go ahead and pull it out to the front and then just worry about the power rule for x to the 6th. All right. Now, the power rule says that the integral is going to be x to the 6 plus 1 over 6 plus 1. And because I don't have any bounds, this is what we call an indefinite integral. And all that means is we're not going to get a number as an answer, but we need to have a plus c at the end because this is basically going to be a function that tells us how to find the area under the curve. Okay, so when we were talking about derivatives in the last class, we were talking a lot about slope, but anytime we're talking about integrals, we're really talking about the area under a curve. Okay, now we'll go ahead and clean this up a little bit. We should get 7 times x to the 7th over 7 plus c. Excuse me. But this 7 and that 7 can reduce, and so we'll just get x to the 7th plus c as our integral here. All right, let's get that all on one screen. Hopefully this one didn't seem too bad. It's just a regular old integral. We'll see a lot more complicated ones, but it's going to be really important that we feel good with the basics here. All right, let's take a look at number 2. Okay, so for number 2, I'm going to go ahead and rewrite this function just so we can see any powers that we might want to see a little bit better. Okay, so here's what I mean by that. I'm going to write this as 4x to the negative 1. Okay, because we have that x in the bottom, and so we want to think about that power being 1, but when we move it up to the numerator, it's going to be the power of negative 1. Plus, in that last video, we talked about how to write the square root of x, and that one is going to be x to the 1/2 power, right? And being able to do this is going to be super important for us to just like know how to do it, okay? It's okay if you need a little review, but please take the time to do that because I think it will pay off in this class. All right. Now we get to use our rules. And one thing I like to do is kind of set myself up to be successful. I know I want to use the natural log for this one because of that negative 1, but for the x to the 1/2, I'm going to use the power rule, okay? All right, let's see what we get. We get 4 times natural log of the absolute value of x. All right, now I don't know what your previous professor said, and I think I said for myself even, like I wasn't really super picky about it, but now that we are in the next class, I really do want us to have those absolute value bars here, okay? Plus, the power rule says we've got x to the 1/2 plus, I'm going to go ahead and write it as 2 over 2 over 1/2 plus 2 over 2. And once again, I don't have any bounds, so I have to make sure I have a plus c at the end. All right, let's clean this up a little bit. 4 natural log of the absolute value of x plus x to the 3/2 divided by 3/2 plus c. And one last thing here, if we are dividing by a fraction, it is the same thing as multiplying by the reciprocal, which means we can write this as 4 natural log of the absolute value of x plus, let's see, the reciprocal of 3/2 is 2/3 x to the 3/2 plus c. All right, and we're going to take it one more step. How do we get this back into a radical form? Because that's the way the question was asked. Ooh. 4 natural log of the absolute value of x plus 2/3. And I'm going to squeeze this in a little closer so it won't go over the line later, but it'll be the same thing as the cube root of x squared plus c. Okay, so let me just shrink that a little bit so we can have it all fit. Really should have just left myself more space here, huh? All right, let's take this one, move it down here, and there we go. Okay. So final answer, we always want to respond in the way that a question was asked. And so since it was given to us with radicals, we want to make sure we go ahead and answer in radicals. Okay. All right, let's take a look at number 3. Okay, so I'm going to use the same approach that I did for number 2, which is I'm going to write this as x to some power so that I can see what that power is. And since I have a constant up here, that 17, I'm actually going to bump that out to the front as well. So when I rewrite, I've got 7 times the integral of x to the negative 2 over 3 dx. Okay. Now I just want to take a moment and make sure we know how we got from here to here. So kind of in my head, I was like, well, I know that x squared and the cube root of that is the same as x to the 2/3. But the reason why it is negative is because this was initially in the denominator. And so when we bring it up to the numerator so we can see the power, it is negative. All right, we'll just kind of squeeze that in there. Okay, so looks like a case of the power rule. We'll get 17 times, let's see, x to the negative 2/3 plus 3/3 over negative 2/3 plus 3/3 plus c. All right, let's clean this up a little bit. We've got 17 times x to the negative 2/3 plus 3/3 is 1/3 over 1/3 plus c. And then what same thing as before when we divide by a fraction. So dividing by 1/3 is the same as multiplying by the reciprocal, or it's like 17 times 3 over 1, x to the 1/3 plus c. And now we'll clean it all up. We'll multiply things out. And I believe we get 51 times the cube root of x plus c. Okay. Now I think this ability to go from x to the 1/3 to the cube root of x is going to be really important because, I mean, the reality is we are an online class. And so when you're looking at other online resources, I want you to make sure you're like, okay, I thought the answer was x to the 1/3. Why are they giving x, the cube root of x? I just want us to know where that comes from. Okay. All right. Any folks out in the audience have any questions so far? Or are we okay to keep moving along?
I'm okay. Thank
Okay.
you.
All right. Sounds good. We're going to go ahead and move on to example 4. So kind of the same shtick that we've been doing. We want to make sure that we write it in a way that we can see the power. So I'm going to write this first integral as 10x to the negative 2 minus 3x to the negative 1 dx. And if we take a moment to kind of compare this to example 2, we'll see that for one of them, we're going to need to use the natural log, but the x to the negative 2, we're just going to go ahead and use that power rule. Okay. So it's okay for us to have to use different rules in the same problem. All right. So power rule says we've got 10 times x to the negative 2 plus 1 over negative 2 plus 1. And then the second part, minus 3, but the integral of x to the negative 1 is just natural log of the absolute value of x. Once again, we're going to stick a plus c at the end because we have an indefinite integral with no bounds. All right. Let's simplify this a little bit. We're going to get 10 times x to the negative 1 over negative 1 minus 3 natural log of absolute value of x plus c. And then we'll go ahead and clean up all of our constants and we'll get negative 10 over x minus 3 natural log of the absolute value of x plus c. And we've got that right there. Okay. All right. We'll keep moving on to the next two. I promise things are going to get a little bit more interesting, more than just the power rule and natural log. Okay. All right, let's take a look at example 5. So when we look at example 5, the first thing I want us to think is, oh, shoot, we don't know a quotient rule for integrals, which is true. We don't, okay? So this is a great example of when it looks kind of complicated. That's not how you spell algebra. All right. But if we lead with some algebra first, we can actually take this and turn it into an expression where we can just use the rules that we already know. All right. So here's what I mean by this. When we have a single denominator and multiple numerators, we can actually break this single fraction into like 3 different fractions in this case. And what I mean by that is we can write it like 3x squared over x squared. That would be the first fraction. Plus x over x squared. That would be the second fraction. Minus x to the 4th over x squared dx. Okay. And so I would encourage you, we are going to learn more rules, and that's fine. They'll have their day and their time. But if we can do algebra and just use the algebra and the basic rules, might actually make our life a little bit easier. Okay, so let's keep simplifying here. In the first one, 3x squared divided by x squared just gives us 3. In the second one, I'm going to have 1 over x. And in the third fraction, I'm going to have x squared over 1. Okay, so we're using those exponent rules that we talked about in the derivatives video. And when we look at this, we're going to have 3 terms in our integral. This one, we will be using the natural log, though, and not the power rule. Okay, integral of 3 is 3x plus integral of 1 over x is the natural log of x. Plus the integral of x squared is x cubed over 3. Indefinite integral means we need a plus c on the end. Okay. All right. Give you a moment to finish writing that down, see if you have any questions, and then we're going to go ahead and move on to our example number 6. All right. All right. So for example number 6, again, kind of looks complicated, but let's lead with our algebra. And the reason why, not just because it's a fraction, but because kind of like the last one, I just see one term in the denominator. All right. So we're going to lead with our algebra first, see how far that gets us. And now we're going to split this into not 3 fractions, but 1, 2 fractions. Okay. So we'll end up with x to the 4th e to the 2x over x to the 4th minus 4x cubed over x to the 4th dx. Okay. Well, we're going to reduce using our exponent rules like we did in the last question. We'll notice that x to the 4th and x to the 4th completely go away, and we just have 1 on the top and 1 on the bottom. Now in the second fraction, though, 3 copies of the x are going to go away, but we're still going to have 1 in the bottom. Okay? And so when we clean this up, we'll have the integral of e to the 2x minus 4 over x dx. All right. Now, it isn't that I love natural log so much, but I just really want to drive home a point that like we can't use power rule whenever we have just a power of 1. So we are going to need natural log for the 4 over x integral, but we are going to need our friend u sub for the very first time today in that first part. Okay. The reason being, and let me highlight this literally, that 2x, it's not just an x, okay? This is kind of like the chain rule that we talked about in the derivatives video. Anytime that power for e is not just x, or we have something that's just not just x, it looks more complicated, chances are we'll need either chain rule for derivatives or u sub for integrals, okay? Now this is, I think, a good time for me to write this as two separate integrals, just so we can kind of see how the setup for our u sub is going to work, okay? So when we set up our u sub, the most important thing is thinking about what is our u. And so in this case, our u is going to be that power, all right? I like to then find the derivatives of both sides. So the derivative of u is du, and the derivative of 2x is not just 2, it's 2 dx, okay? That's really important for us because this dx is really that dx. And so when we're doing substitution, we need to have something to substitute in for. But when we look at this question, like I just see a dx, so I want to get this dx all by itself. Well, how do I do that? I got 2 times dx. So if I divide the 2 away, I'm going to get 1/2 du equals dx. The nice thing about this, it means everywhere I see a dx, like this dx, I can just replace it with 1/2 du. Okay, so we're making a literal substitution. Everywhere I see the dx, I'm replacing it with 1/2 du. Okay, so if we don't write the dx here, then it's like, what are we substituting in for? It doesn't quite make sense. Okay, so let's go back to the question at hand. If I want to do this u sub now, I'm going to get the integral of e to the u times 1/2 du. All right, so there's my substitution. Instead of the dx, I put 1/2 du, and grab a different color. Instead of 2x, I put a u. Okay. And then the second integral, we don't need to use any u sub, so we could just keep it like that for now. All right. I'm going to go ahead and pull that 1/2 out to the front. I know the integral of e to the u is e to the u. Minus, I'm going to pull the 4 out to the front, natural log of absolute value of x plus c. All right. But before we box in this as our final answer, we have a u in there right now. We got to put in whatever that x was back in first. And then so we'll end up with 1/2 e to the 2x minus 4 natural log absolute value of x plus c. Okay. So let me get 5 and 6 on one page for you there, but we've kind of ramped it up a little bit. We got to use some algebra. It's not as straightforward. And we've also seen our first proof at u substitution. How we doing out there in the cyber world? Do we want to have any questions before we take a look at the next 6? And your folks are welcome to use the chat or speak up. Either way is fine with me. All right, cool. All right, let's take a look at number 7 then. All right, now I've kind of prefaced this by saying we're about to dive into a whole lot of u sub, so I hope it's not a surprise that we're going to use u sub for this question, okay? But the indicators that are telling me that I see a function 1 plus x squared and at least part of its derivative, right? The derivative of x squared is 2x. That's how I know I'm thinking I should be using u sub, okay? All right, so I'm gonna let that equal 1 over x squared. I'm gonna take the derivative of both sides. du equals derivative of 1 is 0 plus derivative of x squared is 2x dx. And if we stick to our color coding, what that means is we have our 2x dx, right? And see at 2x dx, I can replace that with du. And everywhere I see a 1x squared, I can replace that with u. All right, so everything's taken care of. I've substituted everything. Now I have just an integral with u's. So the integral of 1 over u du. All right, I really do love those natural logs because this is, again, the one time we're not going to use power rule. Integral of 1 over u is the natural log of the absolute value of u. And I got to be polite. Everywhere I see the u, I'm going to put back in what I started with. So natural log of 1 plus x squared in absolute values plus c. Okay. Pretty classic u substitution kind of problem. All right, let's take a look at example number 8. Now, again, I'm looking at this and I'm like, I mean, it kind of looks like last time, except for I have a square root on the bottom now. But some of those characteristics are the same, and those are the ones that make it so that I can actually use u sub. And that is, I see x squared plus 9, and I know that the derivative of that is 2x. And so because I see a function and at least part of its derivative, my brain is thinking, I want to use u sub, okay? So u is going to equal x squared plus 9. du is 2x dx. And that means everywhere I see 2x dx, I can replace it with du. And everywhere I see x squared plus 9, I can replace that with u. All right, let's make our substitutions. We're going to end up with the integral of 1 over the square root of u du. Now let me just zoom back out for a moment and compare 7 with 8. So when I was writing these examples, I was choosing carefully because I don't want us to now say, oh, it's a natural log in number 8 just because it was a number 7, right? The reason why this one was a natural log is because that power of u is 1. The power of u is not 1 here, so I can't use natural log, okay? So instead, I'm going to be patient. I'm going to rewrite this with its power, u to not just the 1/2, but actually the negative 1/2 power, because the u is on the bottom, gu. All right, we use our power rule. We're going to get u to the negative 1/2 plus 2/2 over negative 1/2 plus 2/2 plus c. I believe when we clean that up, that gives us u to the 1/2 over 1/2 plus c. We are dividing by 1/2. That is the same as multiplying by a reciprocal, which is 2. So I have 2 times the square root of u plus c. And my last step, everywhere I see the u, I'm going to replace it with my x squared plus 9. So I'll end up with 2 square root of x squared plus 9 plus c as the integral of what I started with. All right. So we ramped it up a little bit with the U sub. How we doing out there? Still pretty good, right? Cool, cool. I mean, if these questions are looking straightforward or like things you've seen before, it just means that whoever your previous professor was did a good job in preparing you and making sure that you know how to do these techniques, okay? All right, so let's take a look at number 9. Now, we have a few options here. If we really wanted to go bananas, we could take 4x plus 3 and multiply it out 10 times and then have the integral of that whole long thing and then integrate each term. That is a choice. I don't think it's the best choice, but it is a choice, okay? But the benefit of things like having U substitution is it kind of saves us from having to do that much work, right? This is what I like to call the sneaky version of the U sub, right? Because this is not just x to the 10th. It's like 4x plus 3 to the 10th. And so if we let u equals 4x plus 3, when we find du, we'll get 4 dx. And sometimes when we're looking at the original question, you're like, oh, well, I see 4x plus 3, but I don't see a 4 anywhere. And that's fair. You don't technically see the derivative, but since this is 4 times dx, I can do like I did in that previous problem, divide that 4 over to the other side, and now I've actually matched that dx perfectly, okay? So I'm going to divide that 4 over. I get 1/4 du equals dx, and that means that everywhere I see a dx, I can replace it with 1/4 du, and everywhere I see the 4x plus 3, I can replace that with a u. All right. So that should leave us with the integral of u to the 10th. All right. Now I want to pause for a moment because this 10, you'll notice I didn't highlight it, which means it still should be in your actual problem. All right. So u to the 10th times 1/4 du. Now, for a lot of us, if we felt really comfortable in our previous math class, we might feel fine bumping that 1/4 out to the front right away. No problem. 1/4 the integral of u to the 10th du. We're going to use our power rule here. 1/4 times u to the 10 plus 1 over 10 plus 1 plus c. Let's clean this up. So I'm going to have u to the 11th over 4 times 11, which is 44, plus c. And we just got to put back in whatever our u was. So we'll end up with 4x plus 3 to the 11th power over 44 plus c as our integral. Okay. All right, I'll give you a moment to write that down. I know sometimes I write really fast, especially when I'm by myself in my office, so feel free to ask me to slow down at any point. But in a little bit, we're going to take a look at number 10. All right, so for number 10, if this was e to just x, e to the x, we would be done. It would be e to the x and we would be great, okay? But again, kind of like a sneaky situation, I have something that's not just x. That suggests I'm going to need u sub. So u is negative 0.01x and du is negative 0.01 dx. Now again, carefully chosen problems here by yours truly. I didn't see the 4x dx over here, but I could divide that away and then match the dx. Same thing here, okay? I only have a dx, so we need to divide this to the other side because it's negative 0.01 times dx, okay? And when we do that, we're going to get negative 1 over 0.01 du equals dx. If you'd like, we can turn this into a decimal or into a actual number. If we turn 1 over negative 0.01 into a more simplified version, I believe we will get negative 100 du equals dx. And all that means is that everywhere we see a dx in the problem, we can replace it with negative 100 du. And everywhere we see negative 0.01x, we can replace that with u. Okay, so let's make those substitutions. We'll end up with, and I'm actually going to go ahead and bring that negative 100 straight out to the front this time, okay? Negative 100 integral of e to the u du. Lucky for us, integral of e to the u du is just e to the u. And so we'll get negative 100 e to the u plus c. And last thing, we got to put back in our x that we started with, and we'll get negative 100 e to the negative 0.01x plus c. All right. So I tried to choose questions that, even though they look so different, they actually use the same technique. It's just the actual rule at the end is different, right? This example 9 used the power rule, whereas this example 10 used our exponential rule. All right, we got 2 last problems to take a look at today. And let's see. All right, so example 11 says x squared times x to the third minus 2 all to the 5th power. And I know we've been on a u sub train, but the thing that's telling me I want to be on that train is I see x cubed minus 2, and I know that the derivative of x cubed is 3x squared, okay? If this were not here, I would have to choose a different technique. Or if this x squared was like x to the third or x to the fourth or x to the 17th, I would have to choose a different technique, okay? All right, let's let our u be x cubed minus 2. Du is 3x squared dx. And since I only see x squared dx, I'm going to divide that 3 to the other side, and I'll get 1/3 du equals x squared dx, which means that my x squared dx gets replaced with a 1/3 du. And my x cubed minus 2 gets replaced with the u, and my 5 should still be there when I do my substitution. All right, this is going to give me 1/3 the integral of u to the 5th du. Okay, all we need is our power rule now. So we've got 1/3 times u to the 5 plus 1 is 6 over 5 plus 1 is 6. All right, we're going to clean up our fraction a little bit. We'll get u to the 6th over 3 times 6 is 18. And then we got to substitute back in for our u, and we should end up with x cubed minus 2 to the 6th over 18 plus c. Okay. Now, because I didn't address this earlier in the video, if you're looking at like how I've written it as a single fraction and you're like, hey, Judy, can I write it as 1/18th times x to the third minus 2 to the sixth? Like this is the same as that. It doesn't matter to me which way you write it. I think most textbooks print it like this so they save a little bit of space and they can fit more things on a line. But if you prefer to have your fraction out in the front, that's absolutely fine as well. Okay. All right. Last but not least, let's take a look at example number 12. All right, example number 12. Well, that sure does not look like an integral that I know how to do using like something like a quotient rule because we don't have that in our subset of knowledge, okay? So let's instead ask ourselves the U sub question. Do I see a function and at least part of its derivative in the integral? X cubed minus 3x plus 7. I know that the x squared is like part of the derivative for x cubed, so let's just kind of set it up and see, okay? So u equals x squared, oh no, x cubed minus 3x plus 7. And du is going to equal 3x squared minus 3 dx, okay? Well, 3x squared minus 3 does not match x squared minus 1 until we think a little bit more cleverly. So you notice how both terms have a 3. I can actually pull that 3 out to the front. I can factor that 3 out. And I'll get du equals 3 times x squared, there it is, minus 1 dx. And now when I think about what I want to match in my equation, I have x squared minus 1 dx, x squared minus 1 dx. Okay, so I just have to be a little bit patient there and trust that I know if I see a power and one smaller power, I might want to try u sub as my first go. Okay. Last thing I'm going to do here, I'm going to take this 3 and I'm going to divide it to the other side. 1/3 du du equals x squared minus 1 dx. And x squared minus 1 dx can be replaced with 1/3 du. And x cubed minus 3x plus 7 can be replaced with u. All right. I hope it's okay. I'm going to go ahead and pull that 1/3 straight out to the front so we don't have to worry about it later. The integral of 1 over u du. Okay. I hope by now I've made my point. This is not a power rule. This is actually going to give us our 1/3 natural log of u plus c. Okay. But if this were any other power here, 2, 3, 15, 1/2, 2/3, any other power, we would have to use power rule. Okay. All right, let's finish up our substitution. We get 1/3 natural log of x cubed minus 3x plus 7 plus c. Or if you wanted to be like a textbook and kind of stack that as a single fraction, you could write natural log of x cubed minus 3x plus 7 over 3 plus c. But either version is fine by me. As long as you've got that natural log, you've got the absolute value, you're good to go. Okay. So I hope that this was a good overview of like sort of where I'm hoping that we are or we can get to as we start the course, because our first chapter is all about techniques of integration. We're going to learn what do we do if we can't just use regular rules or u sub? What are some other rules that we're going to learn? And so that'll be coming up in the next few weeks. We'll talk about different rules. There won't be quite as many as we had for derivatives in Calc 1, but we are going to learn some new rules. And so it'd be really important to know, like, do I need U sub or not? Because U sub is oftentimes a little bit easier if we can use it. All right. So if we can't use it, our hand is forced. We'll have to choose a different technique, but listen up in the next videos for like when to use what. Okay.